In the last lesson, we looked at the shapes of different molecules based on the valence shell electron pair repulsion theory. The idea being that valence electrons would arrange themselves in a way that minimizes their repulsion to each other, influencing the shape of their molecule. Lone electron pairs also influence the shape, as their repulsion to each other minimizes the space in which shared electrons take. We also looked at polar bonds, which is to do with the electronegativity of the atom. This causes polarity in molecules as there is an uneven charge distribution. For example, in the HCl molecule, when exposed to an electric field, it tends to line up. The melting and boiling point of covalent molecular substances are really low, which implies that the attraction between them as molecular solids is extremely weak, that is, in comparison to metals and ionic substances. The forces between these molecules are known as van der Waals forces, named after a Dutch guy who tried to explain them. They can be broken into three types. If two polar molecules like HCl meet up, they tend to orientate themselves in a way that the positive end of one molecule is close to the negative end of the other molecule. This neat orientation is more pronounced in the solid state, whereas in the liquid state, the orientation would be random. This also allows us to intuitively say that, or why solid HCl would melt at, say, negative 114 degrees, whereas solid sodium chloride melts at 801 degrees. Just because there are molecules out there that are non-polar doesn't mean that they don't experience intermolecular forces. Take oxygen for example. It is non-polar, yet can be in a liquid state if it's cooled down. This suggests that there is some super weak attraction. So how is this possible? Dispersion forces are like dipole-dipole forces, except that they are temporary. In other words, if we were able to take a slow-mo of the valence electrons surrounding the oxygen atoms, there would be moments in which the electrons would be closer to one side of the oxygen atoms, creating a slightly negatively charged region. This creates a temporary polar molecule, as the opposite side would also experience a slightly positive charge. Therefore, an extremely weak intermolecular bond is created. Dispersion forces increase with the mass of the atom, as the number of electrons involved increase the strength. Hydrogen bonds are the strongest of intermolecular forces. This occurs when a hydrogen atom, which has a very poor electronegativity, is attracted to either fluorine, oxygen, or nitrogen, H1, as these are the most electronegative atoms. This makes for a very polar bond, as the shared electrons are strongly attracted towards a more electronegative atom. Because of this, the hydrogen atom in these circumstances has an appreciable partial positive charge. It experiences a strong attractive force with lone pairs of electrons on oxygen, nitrogen, or fluorine atoms of nearby molecules. Also, a lot of energy is required to break this force, which means melting and boiling points are much higher when compared to dipole-dipole and dispersion forces. In fact, melting and boiling point increase with molecular mass because of this.